This is Mr. Parvaiz with the Henrico High School, and this is Work Lesson 2. In this lesson, I'm going to be connecting the idea of work to kinetic energy. In the next lesson, I'll be connecting the idea of work to gravitational potential energy. So basically what I'm going over is something that's gone over in your book, and they call that the work kinetic energy theorem. They're basically connecting the two concepts of work and kinetic energy to each other. Now remember, kinetic energy is the energy you have when you're moving. So any object that's in motion has kinetic energy, and the equation to calculate kinetic energy is K equals 1/2 mv squared. Your K stands for kinetic energy, your M stands for mass, and your V stands for velocity. If your mass is in kilograms and your velocity is in meters per second, your kinetic energy will come out to be in joules, which is the same unit for work. Because remember, work is directly connected to energy, because you need energy to do work. So kinetic energy is measured in joules, gravitational potential energy is measured in joules, work is measured in joules, as long as your mass is in kilograms and your velocity is in meters per second. So how does this relate to work? Well, simple idea I'm going to introduce to you with the help of a car that's going to accelerate. So you have a car that has a mass of 1,000 kilograms and it's moving, its initial velocity is 5 meters per second, and this car accelerates. So this car's mass has not changed, of course, because the mass is still 1,000 kilograms. However, it's accelerated, so its final velocity has increased. Its final velocity is 7 meters per second. So if somebody asks you how much work was done on this car, well, one of your methods to calculate work is using force times displacement. However, what if you aren't given the force and you aren't given the displacement that this car went through while it accelerated from 5 meters per second to 7 meters per second? Then what are you going to do to calculate work? Well, the answer to that question is you use your work kinetic energy theorem. You use the equation that connects work to kinetic energy. And that's basically the equation for work and kinetic energy, how they're related to each other. When you do work, you change an object's kinetic energy. When you do work on an object, that object will speed up or slow down, but basically its kinetic energy will change. Its energy of motion will change. So I'm going to go ahead and expand this equation further. Whenever you have a delta K, that means change in kinetic energy, and that basically means final kinetic energy minus initial kinetic energy. That's why I wrote the final kinetic energy is just K by itself, and the initial kinetic energy is K naught. I've gone ahead and expanded that equation a little bit further. Instead of writing final kinetic energy, I replaced it with what it stands for, 1/2 mv squared. Now keep in mind that v is the final velocity, because we're talking about final kinetic energy. And when I talk about initial kinetic energy, I do the same thing, 1/2 mv naught squared. So I'm going to have to use the initial velocity. So basically this equation is easy to solve. You simply have to plug in 1,000 kilograms for your mass, and 7 meters per second for your final velocity. And then do that again, 1,000 kilograms for your mass over here, and 5 meters per second for your initial velocity. Remember, the velocity is being squared. The mass is not. The velocity is being squared. You calculate your final kinetic energy, you calculate your initial kinetic energy, you take the difference between both of them, you subtract the two, and you will calculate your work. That's the simplest way to calculate work when an object's kinetic energy is changing. Now remember, this case, the object's accelerating, so your work will come out to be positive. The final kinetic energy value will be greater than the initial kinetic energy. So your work will come out to be positive. But if this car was slowing down, if it had a negative acceleration, if it was decelerating, then the work would come out to be negative, because that just means something is taking energy away from the system being the car and the road. So if something takes away energy away from the system, then the object should slow down. It should have a negative acceleration. It should decelerate. I'm going to take this equation a step further also on the next slide. All I did was replace work with force times displacement. So if you know the final kinetic energy, and you know the initial kinetic energy, and if somebody gives you the force because you know the mass of the car and you know the acceleration, if you can calculate the acceleration using your kinematics equations and multiply it with the mass, you're going to get the force. So basically, your final kinetic energy minus your initial kinetic energy divided by your force will give you your displacement. So I just wanted to give you another equation that just shows you so many extra variables you have that you can determine if you know everything else. So this basically is called your work kinetic energy theorem. It connects the idea of work to kinetic energy. Remember to keep an eye on your units. Your mass should always be in kilograms, your velocity should always be in meters per second, your displacement should always be in meters, and your force should always be in newtons. Hopefully this lesson was useful. In the next lesson, I'm going to connect work with gravitational potential energy.